Hello everyone, and let's start today's lecture. We will proceed from the homework question that I have given to you. Many of you have solved it correctly. Still, I'm providing solution to you. So this was a force given to you, and this displaces an object from initial position to final position. So work done by this force we need to find. We know the formula. The work done by the force is going to be integration f dot dr, which can be written in three different integration format: x differently, y differently, and z differently. Then here you need to place the value of fx, which is 2, so that has been placed over here. The value of fy, which is 4y, and the value of fz, which is z cube, and limits has been placed corresponding. For x integration, the limits are running from initial x to final x, so that they are from 5 to 15. Similarly, 6 to 8 for y coordinate, and 0 to 4, 0 to 4 for the z coordinate. Okay, and then they become integration. Then this is going to be integration of 1, which becomes x. This is going to be integration of y, which is y square by 2, and then 2 get cancelled out, so that's a 2 into y square, and this becomes z raised power 4 by 4. Then limit initial to final, and the way we know the limits are solved, we have solved it, so we can solve it similarly, and then after solving you will get this as your answer. So 140 joule or newton meter is the work done. Since this work done is coming positive, then we will say this force is doing this much amount of work. Okay, and as we have talked about, if the work done comes out to be negative, then we say the same amount of work is being done against the force. So this is the language that we follow. Well, after understanding general formula of work done and having some uh, examples, now let's proceed some specialized cases. That means work done by some important forces, that the forces that we have gone through. So here first we are going to consider the work done by gravitational force or gravitation force. So what will be the work done by a gravitation force when an object moves from one location to another? So let's say this is the coordinate system, this is the x direction, this is y direction, z direction is outward to this screen. So that's a three-dimensional stuff. It is such that the gravity is downside, which is against this y. So if we need to write the force of gravity, we will write this force due to gravity as mg. That's going to be magnitude of the force, and it's going to be in minus j cap direction. Why minus j cap? Because this is how we have chosen the coordinate system. This is the force of gravity. Let's say the particle moves from a location to b location. So a location is, let's say, having a coordinates called general coordinates. Let's say they are x1, y1, z1, and it moves from a location to another point b, which has a coordinates x2, y2, and z2, somewhere in the space. So this is the displacement. Now since we know this gravity force is a constant force near the earth's surface, so we are talking about this near the earth's surface where the g remains constant. So the displacement, we will say displacement vector will be r, and that will be ab vector as per vector notation. So you'll find this is going to be position vector of b minus position vector of a, and if we write directly, it's going to be x2 minus x1 in the direction of I cap, plus y2 minus y1 in the direction of j cap, plus z2 minus z1 in the direction of k cap. So this will become the displacement if the body is moving from a location to b location. And since this is a constant force, and we have understood in case of a force is a constant, then the work done becomes work done because of that gravity force. G subscript is simply saying it's a work done by gravity. Since it's a constant force, so you write it as a force due to gravity dot displacement. Integration sign will not be there. This is the simplified version whenever the force is a constant. Now we can go for the dot product of these two vector quantities. So it's mg minus j cap and dot this r vector, which is x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Now we need to use these rules, the rules of dot product. So this is the dot product, right? So as per the dot product, you know the coefficients of z and z will get multiplied, rest will become 0. So it will become minus m into g y2 minus y1. So this will be the work done by gravity. Now this y2 minus y1 is going to be basically talking about the vertical displacement. So this is a vertical displacement, and vertical displacement is also known as height, right? So we will say work done by gravity is going to be work done by gravity can be simplified as minus mgh if y2 is greater than y1. So let's say a y1 is downside here and y2 here, particle goes vertical displacement like this, so this is h. So if it is moving upside, so this is going to be minus mgs. So that becomes the formula. We can remember this as a formula for work done by gravity whenever a particle goes up. However, if the particle goes down, so let me write complete here. This is when object goes up. So height is h. We will use this. If particle comes down, so h will be pointing downside, so this will become minus, and this minus will get cancelled out. Then the work done by gravity will become equal to mgh, and this formula will be used whenever the object is moving downwards. The object is moving downwards. When object comes down or moves down, comes down. So if there's a displacement in the downward direction, so work done by gravity is going to be positive. This is just because if the displacement is downside, gravity is also downside, so the dot product will become positive, hence work done is going to be positive. However, if this displacement is upside but gravity remains downside, then the work done is going to be negative. That's why this came negative for the first case, right? So we will say when object moves up, work done by gravity is minus mgh, or we say mgh is the work that is being done against the gravity, and in this case the work is done by the gravity. So that is the difference. Now if you look carefully at this analysis, then you'll find this work done by gravity depends only on the final y coordinate and initial y coordinate, and of course the weight of the object, right? That means it does not depend the path it has followed. If it let's say if the particle moves from one location to another location by using this path, or maybe this path, or maybe any other path, as long as the initial and final points are identical, then the work done by gravity will remain the same. So work done by gravity does not depend on the path, rather it depends on the initial position and final position. So that's a very important point, and that will be used later on. So we can say work done by gravity is path independent. Path independent. And it depends only on the initial and final points. Particularly it depends on the vertical displacement. It depends on the vertical displacement alone, not the horizontal. It's simply vertical displacement. An important point that has to be noted down. Okay, so this is the work done by gravity. So whenever you find the work done by gravity, just identify the weight of the object, identify the vertical displacement, multiply. If the vertical displacement is upside, put a minus. If it is downside, put plus. Fine. So that's the work done by gravity. Next, let's consider the work done by normal reaction force. And let's say this is a fixed surface. So it's a fixed inclined plane, or say this irregular plane. Let's say consider irregular plane. for general purpose, and we are interested in finding the work done by normal reaction. So we'll say work done by any force if it is normal reaction. So let's write N. This is going to be defined as integration the normal reaction dot dr. So work done by any force is equal to integration that force dot dr. Right? If it is if the object is moving on a plane surface, then the normal reaction will have a same magnitude and same direction. However, if it is moving in this irregular track, then you'll find normal reaction might be changing at every instant because the angle of inclination will be changing. So if you draw the free body diagram, this normal reaction is going to be perpendicular to the tangent at that moment. So at that moment you need to draw the tangent, common tangent, and you need to draw the perpendicular. That perpendicular is going to be normal reaction, isn't it? And at that instant it will be having differential displacement along the tangent. So differential displacement dr is always along the tangent, and normal is going to be perpendicular to the surface, this common surface, right? Though if this is irregular, then you'll find this normal reaction will not be constant, but you'll find this normal reaction and this small displacement, they will always be perpendicular to each other. So you can write it as integration n dr cos theta. Now that's a difficult integration to perform because n is going to be variable dr, but one thing is obvious, this dr and n is going to be perpendicular to each other, so this theta is going to be 90 degree. So even though the surface is irregular, you will find theta is going to be 90 degree. If the surface is smoother, then also it's going to be 90 degree. That means in all kind of surfaces, you'll find theta will remain 90 degree. Since theta is 90 degree, then it becomes cos 90 degree, and you know what the cos 90 degree is. So this becomes cos 90 degree, which becomes 0, so everything becomes 0. That means we can remember work done by normal reaction is going to be 0 as long as the platform on which the object moves is fixed. That means the platform is not moving. So if it is a fixed platform, then the work done by normal reaction is always going to be 0, simply because differential displacement and normal reaction will always be perpendicular at any instant. However, in certain cases you might find that the platform itself is moving. Let's say I draw over here. If somebody says that this is a platform and which is moving in the upward direction, and an object is placed over here, and this object has a mass, let's say the mass is m. So what will be the work done by normal reaction? Is it going to be is to 0? So you say we need to draw the free body diagram. So if you draw the free body diagram, then you'll find normal reaction is going to be upside and its weight is going to be downside, and let's say it moves upside by distance s. Then you'll find the work done by normal reaction is going to be equal to integration n dot r or dr, right? And if it is moving with a constant velocity or constant acceleration or whatever, we have understood, right? So if it is a acceleration, then you will find effective gravity will become g plus a, and if it is moving with constant velocity, then there will be no pseudo acceleration. So let's say acceleration was 0. So if acceleration was 0, then you'll find normal reaction will become equal to mg, right? And it will remain constant throughout. So this will behave like constant stuff. So it will become nr dot displacement. Now then you'll find normal reaction is acting upside, displacement is also in the upward direction, so they will share a 0 angle. So it's going to normal reaction displacement, which is s into cos 0. This is how you can write, and normal reaction can be written as mg. So this becomes m into g into s. This will be the work done by normal reaction when the platform is moving with 0 acceleration, that means constant velocity in the upward direction. Similarly, if the platform is moving in the downward direction, then you will find the work done will become negative because the displacement is going to be against this. And if it is accelerated, so accordingly the normal reaction value will change. But idea will be this, that means work done by normal reaction remains zero as long as the platform on which the object moves is fixed. If the platform itself moves, then the work done by normal reaction is non-zero, right? So we can calculate the normal reaction work done in any situation by using this formula. And in general we will find this is going to be the case. That means work done by normal reaction will remain zero, because in most of the cases the platform on which the object is going to move is going to be fixed or at rest. Okay, so this is about work done by normal reaction in both the cases, when the platform is fixed and when the platform is moving. Now let's consider the work done by a friction force, and that's going to be important. So work done by friction force, let's start with the basic case. Let's say this is a top view and an object moves from location A to location B on the ground. So the object is moving on the ground from location A to location B, and let's say at any instant of time it is here and it's moving like this on this track. This is some general track. So if it is moving like this, then you'll find the displacement is going to be tangential, and since it is going to experience a friction, so friction force is going to be in the backward direction, and it's going to be kinetic friction. Okay, and so we will write the work done by kinetic friction. So we will write work done by friction is going to be equal to integration force of friction dot displacement for from A location to B location. This is how we are going to integrate it. Now force of friction, since it is a kinetic, we are talking about the kinetic friction because it's sliding, so we can say sliding friction, and we know sliding friction is this has a magnitude as mu into normal reaction. So let me write over it. This is going to be integration and friction, which is kinetic here, and dr is going to be just like dr into cos. If you look as a cos, then you will find there will be at any instant there will be this 180-degree angle, because this kinetic friction is acting backside and this displacement is taking in the forward direction. So cos 180 becomes -1, so it becomes minus integration force of kinetic friction is mu into normal reaction and dr. So this is the work done by kinetic friction whenever an object is moving on the ground or fixed surface. Now what you can do, if it is moving on the ground horizontal surface, then normal reaction remains constant. So if normal reaction is a constant, you can take it outside. So we can write if normal reaction is, let's say, mg, because we know normal reaction remains mg as long as the object moves on the horizontal surface or placed on the horizontal surface, then the work done by friction will be equal to mu remains generally constant, so mu is a constant which is coming outside, mg is a normal reaction is a constant which is coming outside, integration dr. Now this dr is integration of this dr without vector, that means this is a distance element, and if you integrate it, so you will find this total distance between A and B. This has to be integrated from A location to B location. So this will be basically the distance covered by the particle. So work done by friction, kinetic friction, is minus mu and g into the distance, which is the distance between initial and which is the distance covered by the particle, that means actual distance. So here s is going to be the distance, or you can say path length. Now here this is obvious that the work done by friction is not only depends on the initial and final location, but also it depends on the path followed by the object, unlike the case of the gravitation. So that important points come in, that friction, work done by friction, let me write in short, work done by friction is path dependent. and the work done by gravity we saw that was path independent. Now this was the simplest case that I have considered when an object is moving on the fixed horizontal surface. Now if it is not a horizontal, then normal radiation will not be mg, and if it is not fixed, that means if it is moving on the another platform, then we need to see what type of friction is. If it is a kinetic, then we will write this as a mu into nr. If it is static, then you know what to do. In case of static, we write the uh, uh, force value equal to the force causing that tendency for relative motion, right? And sometime it is being asked that work done by friction, is it always negative? Not necessary, because it can also act on the object in the forward direction. uh, if it is acting on the forward direction, then you will find its work done is going to be positive. For instance, we have understood that whenever we walk on the ground in the forward direction, so friction acts in the forward direction, and our displacement is also in the forward direction. So we are having displacement s in the forward direction, friction is going to be acting in our feet in the forward direction. Then the work done by friction in this case you'll find is going to be integration f dot dr by the same rule. And f we need to decide what this f is. You are going to get integration f, this is going to be static friction, and it's going to be dr, and it's going to be cos 0. Cos 0 will make it positive, so it's going to be integration f static into dr. How much the value of f static is, that we need to identify depending upon the case. So work done by friction can be positive, can be negative, can be 0 as well. 0 when the object is not moving, right? So or the displacement is not taking place. So work done by friction is not always negative. It can be negative, it can be positive, it can be anything. But how to find this? This is the formula. Find the force, find the displacement, then find the angle between them, then integrate, you will get your final answer, right? Next important force is a spring force. So let's talk about the work done by spring force. Let's say this is spring of spring constant K, has this as a mean position. So this was a mean position or relaxed position, and it has been elongated by x1 initially. Then from x1 it has been elongated to x2. So from this initial position to this final position, how much the work done is going to be. Now we are just considering this one case, and then in all cases you need to consider what is the initial position, what is the final position, and then accordingly you need to answer. So if we consider this is the initial situation, this is the final situation, that means initial elongation was x1, finally it becomes x2. So work done by spring force, if we are writing like this, work done by spring is going to be written as integration force of spring dot dr. This is how you are going to write. From initial position to final position it has to be integrated. Now we know the force of spring force as per the formula is minus kx I cap. If we are considering this is a horizontal, which is I cap, so this is going to be the direction of spring force, because the spring force is going to act in this direction, so minus I cap. Okay, and displacement dr, we have considered this dr is going to be having dxi dyj dzk. So this is going to be dxi cap dyj cap dzk cap. When you are going to put that dot product, then you'll find only I cap coefficients are going to multiply together. J cap and k cap coefficient will become 0. So this will be going to be equal to, if I write directly, it's going to be minus kx dx. And then we need to write what the initial limits are and final limits are. Now this k remains constant, so you can take this minus k outside, and it becomes x dx. Initial position is x1, final position is x2, or you can write xi xf, initial and final. It's also going to work, so it becomes minus k x square by 2. So you can write by 2 over here, and it's going to be x square. Limits are going to be 1 to 2. So work done by the spring force comes out to be equal to minus half k x2, which is final x square, minus initial x square. So this is the formula for work done by the spring force when it is being elongated from x1 position elongation to x2 elongation, right? Similarly, if there is a compression case, you can write the equation for the compression and you can start from here. You can find similar result is going to be there. So this is the final elongation, this is the initial elongation. If it is starts from mean position, that means x1 is 0, then you'll find it's going to become half kx square. So this is going to be a part of it. That means if it starts, it means block from relaxed or mean position and spring elongates or compressed elongates by x, then what is going to be, x1 will become equal to 0 and x2 will become equal to x. So the work done by spring force will become equal to minus half kx square. So minus half kx square is going to be the work done by spring force when it goes from 0 to x, right? Now again, there can be a question like whether the work done by spring force is always negative or is it positive sometime. So you need to see how these signs are coming in, then you can answer it clearly. So what to say, if you are starting from the mean position or from certain position and getting further elongation, then you'll find there's work done by spring is going to be negative because the spring force is going to act in this direction and displacement is in opposite to this. So if the force and displacement are opposite, work done is negative. However, if the particle is moving from extreme position towards here, so if this is the displacement, then you'll find spring force is also going to be in this direction, then they will have the same direction, then the work done by spring force will become positive as well, right? So this is the case when we are starting from mean position or from a certain position where the elongation is yet to take place, more elongation is yet to take place, right? Then it is going to be negative. So sign to see sign, you need to see what type of display, where the displacement is taking place, and you know already where the spring force acts. Spring force always acts toward the mean position, and then you see where the displacement is going. If the displacement is along the direction of force, then you say work done is positive. If it is against, then you say work done is negative. That means you can say if the block is moving towards the mean position, then the work done by the spring is going to be positive. If the block is moving away from the mean position, then the work done is going to be negative. This is to be remembered for the work done by spring force. So we have understood the work done by gravitational force, work done by normal reaction force, work done by uh, frictional force, work done by spring force. There was a tension as well. In case of tension, we need to use just like any other force. So work done by any force is integration that force dot dr, and you can find work done by tension as well. Now for this spring, again you will find this work done by spring force does not depend on the path. That means if you take block from here to here or directly from here to here, you will find the same work done will be there. So you can remember the work done by spring force, is path independent. Very important. So till now we have identified two forces. One is gravitational, another is spring force. They have their work done are path independent. How it is path independent, you can prove over here. If you are bringing like this, that means you are bringing x, this y and z together, but you'll find when you do this dot product, then y and z component, they are getting cancelled out. So only x component survives, hence only initial and final x position determines what is the work done, hence it is path independent. Now so these are important work dones and their formulas that you need to keep in mind. Now let's take an example to understand about these formulas or their applications. So here is the example. It says let a block of mass given 2 kg is placed on a fixed inclined plane with angle of inclination 30 degree. Height is given as a 20 meter. This height initial point to ground. Friction coefficient is also known to us, and we need to find the work done when the object moves from A location to B location. Or we need to find work done by normal reaction. So what will be the work done by normal reaction? So we know the work done by normal reaction is going to be equal to, can we say directly, it's going to be 0 because it's a fixed platform. So whenever this is a fixed platform, the work done by normal reaction is going to be 0, because at any instant normal reaction will be acting like this, displacement will be like this at that instant. So you'll find their dot product will become 0. Now next can be asked, is this work done by gravity, by gravitational force, or simply can be said as a work done by gravity. So what we are going to say, can we say the work done by gravity as per the formula is going to be m into g into vertical displacement. When it goes to b, it only depends from a and b vertical displacement, which is going to be equal to h, and it's a downside. Since it's a downside, gravity is downside, so it's going to be positive. So work done by the gravity is going to be mgh. Now m is given as 2, g you can take as a 10, h is given to us as a 20, so it's a 20 into 20, that is 400 joule. And then let's say this third part, and let me give you third part as a homework for you to answer. Then I'm going to solve in the next video, and it is asking work done by frictional force, or we can say friction. So when it comes from A to B, there's going to be friction acting on the block. So what is work done by friction force on the block? So use the formula that I told you about work done by friction. Solve and give the answer in the comment section, and in next video I will be solving this particular question. Okay, so in this particular video you have learned specific work done by specific forces, and they are important. So make your notes. If there is any question or query, you can ask. Well, that's all for this video. Thank you for watching. Have a great time.